This podcast may contain forward-looking statements that are subject to risks and uncertainties. These forward-looking statements are based on current expectations and may differ materially from actual future events or results due to a variety of factors. For a discussion of factors that could affect our business, please refer to our filings with the Securities and Exchange Commission. All of our statements are made as of today based on information currently available to us. We can give no assurance that these statements will prove to be correct, and we do not intend and undertake no duty to update these statements except as required by law. Welcome to the Enovix Journey to Scale podcast for Wednesday, September 13th, 2023. I'm Kristen Atkins, Vice President of Marketing and Communications. On this podcast, we'll talk to Enovix leaders and management to gain insights and details on the company's progress to build and manufacture a breakthrough in lithium-ion batteries to power the technologies of the future. In this episode, we're joined by Enovix Chief Operating Officer, Ajay Marathe, to discuss the company's most recent manufacturing milestone of kicking off factory acceptance testing of the Gen 2 equipment in August. Hi, Ajay. Thanks for making the time to talk today. How are you?
Good morning, Kristen. I'm well. I'm really good.
Wonderful. Our listeners want to know about our most recent manufacturing milestone, beginning factory acceptance testing in August. Can you bring us up to speed on how you got to this point and its significance?
Sure. Completely thrilled to share with you that in our journey, with the process that we laid out earlier, which was the equipment procurement spec that we follow here at Enovix, it started with design lock-in of the equipment, PO placement. And now the most important milestone is right if we are in the middle of it, called the factory acceptance test. The machines are ready. I showed them at the last, or a glimpse of them at the last earnings call, if you remember, when we did the live streaming. The equipment is sitting there on the floor, waiting for our engineers to really go through a full debug and acceptance of the equipment. So, as you know, the battery equipment that we have, the set of machinery that we have, the auto line we call it, is divided in four particular distinct zones. The first zone being the laser patterning, and the laser patterning equipment basically is made by a particular supplier in Asia, and it's ready for factory acceptance test. It was ready 2 or 3 weeks ago. We started the factory acceptance test in August. It will last all the way until October, then followed by the zone 2 and 3 and the 4. And when we finish all of that, then the equipment gets packed up and shipped to Malaysia, which is the final destination for this machinery to go produce batteries. So we are starting the journey for factory acceptance test now, zone 1 being the first one to start.
And can you walk us through how you got here? Let's start at the beginning. You joined in November. You've made tremendous progress, and you told us that you took learnings from Gen 1 and applied them to Gen 2. Can you walk us through that process?
Indeed, absolutely. So, when I joined Enovix November 14th, we were right in the middle of all the discussions at the time, waiting for the business to be awarded to the suppliers for the Gen 2 equipment. But more importantly, what we learned from Gen 1 is, how to design the machine in order to really, cater to our architecture, to our tolerances, to repeatability, to uptimes, going through every aspect of what makes the machine predictable in high volume environment. And that's what we did. So we applied all that learning, including the yield learning, which was very important, create the design, negotiate with the supplier on their ability to make the equipment, and then settling on a design, which is then locked in, zone by zone, machine by machine. Just as a reminder, there is roughly 36 pieces of equipment actually in this line, Gen 2 line 1, which we are talking about right now. And so it was very important actually to go through every single machine's capability. What is it supposed to do? What is the tolerances? what is the repeatability that we need, from each of the equipment, and lock that design in. Once that design was locked in, we placed the POs. The POs were accepted, and the equipment suppliers just went to work on creating what are called POCs. This was a very important step, which was different than when we did the Gen 1, frankly speaking, because there was lack of time or resources, perhaps. I wasn't here, so I can't really comment a lot on that. But the POC is not a rocket science. It's basically, you create the design, and the design, when it is done, you basically fabricate what is known as a proof of concept equipment, benchtop equipment, which proves out the design. And once that is done, you then buy off the POC, you tweak the POC until you get it right, and you get it perfect, and then you release that as a design lock-in, so that the high volume equipment is then made from that POC. So we created a whole lot of POCs, again, learnings from Gen 1, what went wrong in Gen 1, or what was deficient in Gen 1, how could we, learn from that, and, what POCs we need. So people got busy in basically buying off the POCs one by one, right? And the whole team basically worked very hard, got it to the point where we could lock in the design of the high volume equipment from those POCs, and the design lock-in happened with a lot of rigorous understanding of, is this process capable of doing the 4 or 5 sigma process. 4 sigma process signifies how controlled your dimensions and tolerances are relative to the spec limits, and the variability from one battery to the other is controlled in such a way that the sigma or the variance in the process is minimal, so that you can achieve what is known as a 1.33 or better CPK for each process, which is really the most important thing to achieve in a manufacturing environment. So that's how we got here. The design lock-in happened. I was there when the design lock-ins were happening, actually, at the supplier site. Then the equipment supplier went to work. They built the frames. There was no compromises in how the frames were designed. Perhaps we did a little bit over engineering, to protect ourselves and mitigate the risks of understanding the process itself. And now what we have is a FAT ready Zone 1, which we began the FAT on in August, actually, as the team is going through. Basically what they're doing is they're taking the electrodes as they come in from a coating supplier, mounting it on the machines, and we are laser patterning to the specs that we have to make sure that the patterns are not only dimensionally in the right place, but also the uptime of the machine, mean time between assists, mean time between stops are all monitored, and the machine is ready for the 1350 UPH. That's what is being bought off in the FAT.
All right, so you talked us through a little bit about starting FAT in Zone 1, but I think let's paint a picture of what are the zones, explain how many zones are in a line. If you could walk us through each one, that would be helpful.
Sure, absolutely, yeah. So, for us, all these zones are very intuitive. To a casual listener, we need to really describe it properly. So here it goes, right? So imagine the whole battery line. It starts with the electrodes in a form of a roll, which come in from a supplier, and the last step being the battery is fully tested, sorted, ready to ship. So that's the whole start to finish. Now I will break it down in the process steps. So 4 zones. So Zone 1 is really laser patterning of the electrodes, right? This is where we create our own, pattern, cathode, anode separated, so that we could stack them in the 3D structure. The electrodes are rolled back after they're patterned, back into the roll form, ready to be fed to what is now called Zone 2. Now, what is zone 2? Zone 2 takes the patterned uh, electrodes and as an input, and basically punches each of the electrode strips, which we have carefully laser patterned, are taken out of the electrode, so punched away and stacked. So stacking is the most important first step in zone 2. After the stack is done, it is still in the unibodies, the fixtures with prongs on it, carefully held. The number of wave pairs are stacked, and now we have the battery. The cell is starting to take shape, right? The next step after that is AO apply, alumina overfill, stencil printed, which is applied on the cell. Then the cell, this is still zone 2 I'm describing, and then a bus bar is inserted, and a tap tear process happens, and basically now it's ready for constraint apply. As you know, we have a stainless steel constraint in our battery, which is important to make sure that the 3D structure is held together firmly, so that the swelling is minimized when the charge and discharge of the battery happens.
So that's zone 1 and zone 2. Can you walk us through what happens in zone 3?
Sure thing, Kristen. The output of zone 2, which is really the die inside of a constraint, is now fed into zone 3. The zone 3 itself consists of 2 subzones, zone 3A and zone 3B. And let me explain to you what that means. So zone 3A is first when a pouch is created in which the cell from zone 2 is actually put inside the pouch. Electrolyte is filled in. The lithiation process, which is pattern, lithiation or lithium foil, is put on the constraint. This is a very different process, and only our patented technology of prelithiation is what uses this particular zone 3A. So zone 3A is pouching all of that inside a pouch and sealing the pouch, basically. And then from 3A, the pouch then moves over to zone 4, which is the first formation of the cell itself. In the first formation of the cell, the lithium that we just put on the cell, on the constraint, is now biased, electrically biased between that and the cell itself, so that the lithium traverses through the constraint slots and the porous polymer separator material very uniformly across all the wave pairs or the cell or the die, so that the extra lithium now sits in the cathode waiting for the battery operation to begin. So that's zone 4 beginning, which is the formation. Then the cell gets back to zone 3B. In 3B, the lithium flag which was put in is removed. The electrolyte is refilled and the pouch is resealed, this time to the size of the final battery, right? So that's the zone 3B. So 3B essentially takes the lithiation process complete. Now the recutting of the pouch and forming the exact pouch to the cell. Now the cell is ready. It's in the final form. It is now passed on to zone 4, back again for the charge and discharge cycles and the testing of the battery to make sure it performs the specs that we are shipping to. So that completes the whole battery line.
My understanding is that's industry standard except for the pre-lithiation process. And Enovix does the pre-lithiation process because we use silicon. Is that correct?
That is correct. So you can ask a question, for example, why don't the normal jelly roll pouch cell people use lithiation process? Simply because the structure of the jelly roll cell does not allow itself to have the pre-lithiation done very uniformly. If somebody tries to put lithium on top of the jelly roll, it will only lithiate the top layer and will not go uniformly to all the layers of the battery, which is why they cannot the other normal battery guys cannot do it. We can, and that's what gives us a big advantage over the amount of lithium that is being introduced in a battery, which then gives a lot more energy to the battery. All this entire line has an input output, which is fully automated. It is basically an operator. All the operator has to do is basically dock the mechanism, whether it's a cassette or a cart, which has the constraints. Everything is fully automated. The machine picks and places the stuff onto the battery. It's processed through the line. It's very minimal to almost no human touch in between, right? It's a fully automated line, except for the offline metrology, which sometimes we do just to make sure that the process that is running runs at a very high CPK. So the whole principle of don't make mistakes, don't accept mistakes, don't make mistakes, and don't pass on defects to the next step is followed through the line, right? So we have a pretty robust Poka yoke, which is really the foolproof concept of the line, which we have created in the Gen 2. So that's the whole line description, Kristen.
Got it. Got it. Thank you. Thank you for detailing all 4 zones, which make up one line. And now talk to us about how zone 1 and zone 4 can actually serve multiple lines.
Right. So zone 1 and zone 4 are basically what we call zone 1 is a laser farm. What does that mean? Regardless of the size of the battery, and remember, we are going to make a lot of custom batteries at Enovix because they need to exactly fit the socket that we are going after, whether it's a phone or a wearable or a bigger cell in a laptop or any other medical device or anything. The dimensions are different, and those dimensions difference means the electrodes, the size of the electrodes and number of wave pairs is different. So X, Y, Z are according to the customer requirements, right? So a laser in zone 1 is catering to all sizes, is regardless of any size. Whereas the zone 2 and 3 requires tooling, which is dedicated to that particular battery, which is why once you set it up, then it becomes dedicated to that particular battery which is being made. Whereas zone 1 and similarly zone 4 is basically charge and discharge testing and open short testing, which is in zone 4, which is also a regardless of the size of the battery. So what we have done is zone 1 and 4 are pretty much recipe driven, catering to all sizes, and therefore they are farms. And zone 2 and 3 have dedicated tooling per battery. So a customer comes in with a different battery requirement or size XYZ. Zone 2 and 3 tooling gets done, and it's now on the zone 2 and 3, and that becomes a full line. So 1 and 4 have to be looked upon as a farm, and 2 and 3, which serve multiple lines, whereas zone 2 and 3 will be dedicated to either wearables, which is a lot smaller battery, so therefore higher UPH, or a large cell, which is like a laptop battery. There is no point in dedicating zone 1 and 4 to this, physically. There's going to be AGVs running between lines, by the way, carrying material from one zone to the other, automated guided vehicles between zones, which is, going with the industry 4.0, principles. That's how we have designed the factory.
Got it. Okay. That's helpful. Now, you described the 4 zones, the high volume manufacturing line and its automation. Now, you're building 2 agility lines. What is an agility line?
Okay, so yes, we are building 2 kinds of agility lines. So let me explain what agility line purpose is, right? So there are 2 kinds. The first kind is really catering to a lot of new technology development and new materials development, right? So that's called an R&D agility line. Agility word comes in from us having to do stuff quick, fast, and nimble. And the spec that or the requirements that we are following in our head for the agility line are catering to what the customers really need and being competitive in the market, right? So R&D agility line really is catering to experiments, to development. So it's not really focused on units per hour. It's not the speed which matters in terms of running the line itself, right? We should be able to quickly, convert the line to a certain, size of the electrode or a size of the battery, or a different material set, different electrolyte, etc. So quick, agile from that perspective, but not necessarily when it runs at a very high UPH. So automation is not a focus on the R&D agility line. That R&D agility line is going to be here in Fremont, where most of our R&D resources are located, is going to be running on a very quick turn, R&D experiments which are needed to qualify new technologies. So that's one kind of agility line. Low UPH, relatively very high, good precision tolerance, essentially the same kernel of the tools for zone 2 and 3 as a HVM line or the other agility line, which I will describe here in a moment. But that's what, this R&D agility line. The second kind of agility line is really a higher speed agility line, which is basically making custom cells in hundreds and thousands. So here the UPH does matter. So when we convert the agility line, again, agility line is really zone 2 and 3 only. And why is that? Again, I explained in the prior conversation, zone 1 and 4 are farms. There you can cater to anything. Those are very high speed machines. Zone 2 and 3 is what agility line is all about, right? So the first one, R&D agility, second one being a custom cell agility line, which is going to be running 24/7. It is going to be running more than 100, close to 100 to 200 UPH, and developing and creating batteries which are developed in the R&D agility line, or just the extension of what we already have. So in other words, you have to imagine building blocks called new technology platforms or building blocks, right? It's a different, either it's a special cathode, anode, electrolyte, construction, those are building blocks, right? EX1, EX2 that, we have talked about. Those are once the building blocks are ready, you now need to stitch those building blocks into a product. And that product becomes a customized product for each customer. Agility line number 2, which is the higher speed, continuously running, is creating hundreds, like I said, what we call in our journey of qualification of parts, we call that QS 100, which is quality samples given to the customer to their specs, to their dimensions. And that's the purpose of the second agility line, is to create the batteries, which finally will go into the hands of the customer so that they can start their qualification, right? So that's a higher UPH 24/7 line, zone 2 and 3 again, with the identical kernel as the HVM line. So when a customer qualifies product based on the agility line, it seamlessly moves to the HVM line. So you don't have to repeat the qualifications. And that it was important for that line to be in the same location as the HVM line. So we don't change the location on a customer. When a customer comes in, qualifies product which is made on the agility line, we then take it seamlessly into the HVM line right next door in the same building in Penang, Malaysia, to do the high volume manufacturing. So millions produced on that line. So agility line number 1, R&D agility line number 2, the custom cell agility line located near the HVM line and the HVM line. So 3 kinds of lines, 2 agility lines.
And so that saves the customer from having to qualify on 2 different lines. So that's great. Got it. Okay. So can you walk us through now the timeline for your next major milestones? You've kicked off FAT, factory acceptance testing, in August. And now can you walk us through the timeline for the...
Yes. So the zone one was ahead of its time, and logically speaking, that's how it should work because material made on zone one will be then utilized to qualify zone two, then zone three, etc. That's how the sequence of events works. So zone one ready for FAT, already began FAT 2 weeks ago in August. We will finish that FAT by October. That's how the FAT for zone one is lined up. By the time we finish it, it would have already passed all our UPH requirements, uptime requirements, quality requirements, and it's ready to go. In terms of the next step for the zone one. Zone two will begin FAT in September, towards the end of September this month, and it will go all the way until probably close to the end of the year. That's how zone two is being scheduled. Zone three will begin the FAT around end of October, beginning of November, and also finish by the end of the year. It might slightly go beyond the end of the year and to the first couple of weeks of January of next year, depending on how we finish the FAT from all parameters checking out, and then zone four kind of goes hand in hand with zone three. So we'll be done with all FATs around middle of January, which is when it's supposed to finish. And then as we finish the zones, by the way, the shipments will start happening. As you know, Fab 2 is being finished right now for facilitization. The power incoming, the flooring, everything is being done right now as we speak. That'll finish sometime around end of October. The zone one would have finished FAT by then, and we'll give a green light for the zone one equipment. The lasers that I showed this last time at the earnings call will end up shipping to Fab 2 location in Malaysia. The good news is that the travel time between the Asia site where the equipment is getting manufactured and our Penang site, Fab 2 site, is a relatively short distance. So it'll get there within about 4 to 8 days, and then we'll install it. And then the SAT will begin zone by zone on each of the equipment. It's like a domino. Now, the SAT, as I will remind everyone again, consists of not only buying off the equipment for uptimes and UPHs and takt times, etc., but also a full-on process characterization review, or what we call PCR2, in the journey of procuring and buying and installing the equipment, will be completed to make sure that each process is operating at a CPK of 1.33 or better. And then we'll give the green light for the high volume production to begin on this HVM line. That's our timeline for HVM, Kristen.
Okay, all right. So SAT, which is site acceptance testing, and then PCR2, which is process characterization review. Is that right?
That's correct. Yeah, SAT is basically, we'll do the FAT, which is factory acceptance test, machine by machine. Then the SAT is the first time when all of the machines get connected together in one place, and we'll do a full-blown buy-off of the material flow between machines, the automation, and then the PCR2, which is the process characterization, which is the most important part of the line buy-off, is to make sure that the variability in each of the process steps is controlled to the point where we achieve the process capability, or CPK, which I mentioned earlier, of more than 1.33, signifying at least 4 sigmas away from the spec limit is where the process capability lies. And that's the place we would like to operate the high volume production line at. Similar milestones, but much sooner than this timeline, is on the agility lines. The first one being the Fremont agility line, which is the R&D agility line. The FAT on that line will be done and finished by the end of this year, beginning of next year. The equipment will be here in Fremont. A lot more flexible, type of equipment. Zone 2 and 3 only, as you remember, I just said. And same thing with the Penang agility line. Will finish its FAT and SAT by beginning of next year, and that will be the first one to get installed in Penang, Malaysia.
That's exciting. A lot to accomplish in a few months. So talk to us how you do this. I mean, you've got 4 decades of manufacturing experience. Tell us about the systems that you have in place and what frameworks that you use.
Right. So yes, I'm coming up to my 40th year in the industry on April 16th, exactly to be precise. I'll be done with 40 years, April 16, 2024. So closing in on it. Yes, I've done similar equipment purchases and design and installation, and then the ramp for many large customers, very steep ramp. Consumer products, that's the thing, right? You have to really ramp in a very short period and take it all the way to the highest production output, and then kind of level it, and then the product, particularly the life cycle of the consumer products, typically starts declining, beginning of the following year. So it's a short ramp up and level and a down in which you need to really achieve really high yields and near perfect, zero defects mentality quality. So it all starts with a system in which you're supposed to operate, the operational excellence system, as I call it, right? It always works, and there's no shortcuts for that. There's no, there's no letting up, compromise on one versus the other. So equally important. So I've introduced that here at Enovix now, the framework of operational excellence. I call it, it's easy to remember, name, it's an acronym. It's called DIMES, DIMES. It basically stands for Design for Manufacturability, Design for Cost, Design for Quality. That's a D. I stands for Integral Yield, which is, laser focus on start to finish every process step, how the yields, what is the Pareto, where are you losing parts, how can you learn from, one process to the other, zero defects mentality. That's the integral yield, extremely important to make sure that the quality that the customer gets is really the highest quality. Then the M stands for material cost down. This is also very, very important. As you know, in our battery world, 50 to 60%, depending on the size of the battery, cost of a battery is really materials, bought materials, right? So the focus on second sourcing, multiple sourcing, basically making sure there are 3 really good suppliers for each a commodity that goes in, those types of principles. Value engineering, which is really also equally important, which basically questions every single step that you perform, not only in your backyard but also in your suppliers process, where you can value stream map the steps and take all the non-valued steps out. So M becomes a really important part of the operational excellence, which is material cost down. Then E stands for equipment efficiencies and effectiveness, the OEE, getting more out of the existing installed base. And that has to do a lot with, mean time to assist, mean time between failures, mean time to repair, those types of, and uptime of the equipment itself, right? And designing the equipment to cater to all of these things. So UPH, maximizing, improving and resolving the bottlenecks, those are all, under the E, equipment. And then S is really the supply chain excellence. And supply chain excellence has different, different ways of excelling at the supply, which is really cycle time reduction, making sure your cycle times are no more than 2 to 3 times the theoretical cycle time. That directly affects the inventory and the working capital. And don't have inventories in pockets, do a Kanban system, Those are the supply chain excellence, areas. So DIMES together is again a framework in which operational excellence is measured. I have deployed this in several companies, large companies that I've worked for, and it is being deployed right now. We had our first conference for DIMES 2 weeks ago here in Fremont, where everybody was super excited on how we're going to operate this company going forward. Right? It's a proven technique. It gives a purpose to everybody in operations and creates this cross-functional teamwork, which really gets the best out of people. So that's the plan.
That's great. What gives you confidence that Enovix is going to scale?
So multiple proof points, right? So Gen 1, when I first joined the company, Gen 1, the equipment here in Fremont where I'm sitting was pretty much, people had given up on it. It's just not performing. It had all kinds of issues. The design was not done properly. The tolerances are not being met. All that is, those are a lot of beliefs and opinions. Applying the principles which I just talked about, learning from it, learning so that you don't make the same mistakes again. We have been able to now ramp that yield, which was a low single-digit yield, to a fairly decent number. That in itself has driven tremendous amount of confidence to the team, right? That we can actually perform. Even in a substandard designed equipment, we can achieve those kind of results. Number two, gives me confidence that we have done enough work with the material suppliers now that we are able to go and have access to the best cathode. Remember, Enovix architecture is material agnostic, which means we can really go after the best cathode, best anode, and separator, and incorporate that into our structure, into our technology, and produce some phenomenal results. So we have shown now that we have access to some of the best materials out there. We were 3 generations old when I first started here in terms of materials, right? Now we are getting the latest material from all these suppliers, and suppliers are deeply interested actually in supporting us. So that's a second proof point of confidence. The third proof point of confidence is really these POCs, which I talked about in Gen 2. Looking at these POCs operate. Can I insert the bus bar repeatedly, millions of times, very fast? Can I laser pattern with the tolerances that I need on the fly without having to stop, the machine or the material in order? Can I do that? And we have seen that now being demonstrated. Gives me a whole lot of confidence that we understand what it takes actually to do this at a high speed. 1350 UPH, which is the first universal line UPH that we are signing up for, or we have signed up for, it's within our grasp right now, right? So that gives me the third confidence. And then of course, doing this in my old stomping ground, which is Penang, Malaysia, where like I said, showed up there first time, and we were able to hire 30 people of the best people of different kinds, disciplines, process people, maintenance people, equipment engineering guys, quality people, reliability people. Within a week, we were able to spot and hire. That gives me a whole lot of confidence that we are doing the right thing.
Thank you so much for taking the time to have this conversation with us, Ajay.
Thank you, Kristen, for having me, and hopefully the insights were helpful.
That concludes our first Journey to Scale podcast. Thank you all for tuning in. Be sure to subscribe for alerts. We'll be releasing new episodes as we reach new milestones and scale up to high volume manufacturing. Until then, thank you and have a great day.